Hello YouTube, this is my fourth video on my module on logarithmic functions. In this one we're going to focus on the graph of the parent function in general. And so I just hope to get a few things across, like by the time you're done watching this you should be able to know where the asymptote of the graph of a logarithmic thing is, the basic shape of the graph of a logarithm, maybe one of the intercepts and how it kind of proceeds, okay? But in order to do this we're going to start by kind of considering this. We're going to say to sketch the graph of y equals log base a of x in general, any log base a of x, we'll say this is our parent function here, is a parent function, okay? What we're going to do is we're going to use the fact that it is the inverse of the graph of y equals a to the x, okay? So we say we can use the fact that inverse functions have domains and ranges that are switched, okay? So the x's and y values are switched, and have graphs that are reflected about the line y equals x. Recall that any inverse functions are reflected about this identity function, okay? So in order to graph, say y equals log base 2 of x, okay, which by the way, if I sketch over here, we say y equals log base 2 of x, okay. If I rewrite this in exponential notation, we could say the same thing as this. We say our base. Well, what's our base? Our base is 2, okay. 2 to the what power turns into x? Well, 2 to the y, this thing turns into x. So we get 2 to the y equals x. So looking at this and looking at the function y equals 2 to the x, this is y equals 2 to the x. Which we already know what that looks like. We're going to graph this one and then going to kind of get an idea of what 2 to the y equals x looks like just from that, okay? So we'll start by graphing f of x, which is our 2 to the x power, you know. So if I said, you know, I like to plug in 0 first, we say 2 to the 0, we get 1, okay? 2 to the 0 is 1. 2 to the 1 is 2. 2 to the 2 is 4. Going backwards, we say 2 to the negative 1. Recall that 2 to the negative 1 is the same thing as 1 over 2 to the positive 1 is a half. So we get a half here. And then if we plugged in negative 2, it's the same thing as like the 2 to the 2, which is 4, but it's its reciprocal. But we say 2 to the negative 2 for those who want to see the algebra here. It's the same thing as 1 over 2 to the positive 2, which is a fourth. Excuse me, so we get a fourth. So we're going to go ahead and sketch this in. I'll sketch this in red here, but we say we had an intercept at 0, 1, 0, 1. We say 1, comma 2, and we plug in 1, we get the value of a, which is our value of our base here. We say 2. And then we'd say, okay, so at negative 1 we had a half, at negative 2 we have a fourth, and so this is our graph right here. At 2 we had 2 to the fourth is 4. This is our exponential graph. So we say of all exponential graphs, I got to be honest, you know, up until this point, we should just know by heart that exponential graphs that haven't been translated have horizontal asymptotes that are on the x-axis. Here we say at y equals 0, has an intercept at 0, 1, 0, 1. This is a very important point. And then went through the point 1, comma a, in which our a value, our base value is 2. Should just know these. I mean, if you know those three things, you can sketch pretty much the entire graph. What we mentioned, though, was essentially this. I'll get that out of the way here. We said, okay, so if we're going to graph the inverse, which is this log y equals log base 2 of x, which is the same thing as 2 to the y equals x, well, first of all, it's reflected about this line y equals x. So if I, you know, in purple here, y equals x has an x-intercept, you know, y equals 1x plus 0, you know, slope-intercept form, has a y-intercept of 0, goes up 1, right 1. So basically, I'm just going to kind of sketch this in here. We say, here's our identity function, y equals x, about which our original graph is going to be reflected because we are graphing now its inverse. Also this, we say, well, if the original table looks as it does here, then we could necessarily say this, well then y equals log base 2 of x. This is really shabby how I'm throwing this together, and I apologize, but has a domain and range that are just switched. So that means all of our x's and y's have been switched. So instead of negative 2 comma 1/4, we have a fourth comma negative 2, and we have a half comma negative 1, and we have 1 0 and 2 1 and 4 2, because all of our x's and y's have just been switched. So if we graph these now, we say when x is a fourth, and x is in a fourth here, we say we're just switching this point, then we get negative 2. So we say it'd be about right here. And I should switch my color out to, I don't know, why don't we go like a green-ish. We say negative 2, and we say at a half, we're at negative 1. And this is very important. This point right here, we say 0, 1 is on this graph. Well, then on its inverse, we have 1, 0. We're going to memorize this point today. But we say also the point, let's see, 1 comma 2 is on the original graph, so 2 comma 1 is on this inverse graph. And then 2 comma 4 was on the original, so 4 comma 2 is on this graph. So what we get is this thing right here. We get this function. Let's see if I can make this a little bit better. And it grows very slowly. I mean, if it's the inverse of an exponential thing that grows very quickly, I want you to know that logs grow slowly, very slowly as a matter of fact. And then also this, if there is a horizontal asymptote at y equals 0 on every exponential function, parent function, then there is a vertical asymptote on all of our logarithmic graphs at x equals 0 on all of these. Okay, so this is kind of the basic graph here. As a matter of fact, what I did was I went ahead and I graphed y equals 2 to the x in GeoGebra. You can see that we have a horizontal asymptote at y equals 0. We have the intercept at 0, 1, and in this instance it goes through 1, 2. If I were to draw in now our identity function, which is this y equals x line right here, we say, okay, then our logarithmic base 2 of x function looks like this. And so you'll notice, the original horizontal asymptote has just become a vertical asymptote. Instead of going through 0, 1, it goes through 1, 0. Instead of going through 1, 2 in this instance, since 2 is our base, we plug in 1, we get the value of the base. Then we get, 2, 1 on this graph. So, really easy. If you wanted to graph a logarithmic function, the first thing I'd tell you to do is just go graph the exponential function that is associated with it, graph its inverse, and then we'll just, use its inverse to help graph this. Okay, so kind of to advance our understanding of this, let's take a look at one where we graph the common log. Okay, so the common log, remember common log is log base 10, and we can use a calculator on this one, is what I intend to do. But we say log base 10 of x. And I just want to kind of sketch this off to the side very, very quickly. We say this is y equals log of x. This is log base 10 of x. This is the same thing as 10 to the y equals x. Whoops. So if this is the case, what we should do is we should necessarily go graph its inverse. 10 to the x equals y, or y equals 10 to the x. So if I said, well, y equals 10 to the x, what do I know about y equals 10 to the x? Well, I know it has a horizontal asymptote on the x-axis. This is the exponential function I'm discussing here. It has an intercept of 0, 1, and when y is 1, we get the value of the base here. It goes through 10. So this is a very, very quick growing thing. This is our exponential function that is the inverse of the log that we're going to be graphing in a moment. And we know that it's reflected about this line, y equals x, and I'm sketching this hastily here, y equals x. So if I'm going to graph this, let's go ahead and plug in a few points. I mean, if I've got a calculator to help me do this here, and I do, there it is, there she is. We say, how about this? Plug in a tenth. So we say y equals log of a tenth. Now, we're saying this, y equals log base 10, base 10. I don't need a calculator to necessarily do this one here. We say, what could I take 10 to the power of to get 1/10? Well, 10 to the power of 1 would be 10, so 10 to the power of negative 1 would be 1/10. So I should get negative 1. So negative 1, but I do want to use a calculator to check this out. We say 0.1 common log, negative 1. Okay, how about a half? Okay, so we say 0.5 common log, about negative 0.301. So I have no problem getting out a calculator and typing this in, negative 0.301. Anyone knows how to do math can do that. How about 1? Oh, the log of 1. We should know this one. What could I take anything to the power of to get 1? Should be 0. Should be 0 here, but let's check it out on the calculator. We say, okay, so 1, log base 10 of that is 0. Okay, remember the log of 1 is always 0. What about the log of 5? So we say 5 common log, 0.699-ish. Okay, so we get 0.699-ish. And we say log base 10 of 10. Oh, remember this one. We say log of 10. It's the same thing as common log base 10 of 10. So I'm saying, what could I take 10 to the power of to get 10? Should get 1 here, but again, checking it out on the calculator, we say 10 common log of that is 1. Okay, so anyways, we've got these points. Let's go ahead and graph them in. I'll switch my color up here. We say at 1/10, when x is 1/10, we're down at a height of negative 1. So we're about right here. When x is a half, okay, we're at a height of negative about 0.3, about a third. When we're at 1, 0, okay, 5, when we plug in 5, 1, 2, 3, 4, 5, we're at a height of about 0.7-ish, almost there. And then when we're out here at 10, 10 is actually 1 past my grid here, we're at a height of 1. So you can see that this graph does grow very slowly, and it's drawn very poorly because I'm a human, sorry. But you'll notice here that, again, the important things to notice are just these. Just memorize this about every logarithmic function right now. It has an asymptote that is the y-axis. It goes through the point 1, 0 is its intercept. And in this case, instead of going through 1/10, it goes through 10/1, 10/1. Okay, this is on my graph here, okay? So easy to check that out. Whatever your base is, we could say take the log of that base, log base 10 of 10, you'll get a height of 1. And that's a good point to kind of memorize. So in other words, if I had been doing log base 5, of x, then what I know is this: when I plug in a 5 right here, I would have been a height of 1. But that's another point to memorize. Okay, so things in general about this graph we would like to know in general. Let me pull this up for you here. These are things you'd want to necessarily know in general. We say, since the logarithmic graph of the function y equals log base a of x is an inverse with y equals a to the x, then we can draw many conclusions about their graphs from knowing what we know about the exponential function. So knowing what we know about the exponential function, recall, if I go look at the exponential function, we say, well, the domain is all real numbers. Domain is all reals, but its range is just from 0 on up. It only uses y values from 0 on up, and it doesn't include 0 because we have an asymptote on the x-axis. So just knowing that, what I can tell you about the logarithmic function is domain and range are switched. So instead of domain being all reals and range being from 0 up to positive infinity, we have domain from 0 out to positive infinity on the right on our x-axis, and the range is all y values. It covers all y values, and instead of having an intercept at 0, 1, it has an intercept at 1, 0, and instead of having a horizontal asymptote at y equals 0, it has a vertical asymptote at x equals 0. All of these things are present on this list here. So there's good things to scribble down, but we say notice the domain is on our x-axis. The inputs that work are 0 out to infinity, and we do not include 0. Remember, you can't take the log of 0. You couldn't take anything to the power of anything and get 0. We say the range is all real numbers. We use all y values. The x-intercept is 1, 0. It's always increasing. Okay, it is 1 to 1. It passes the vertical line test. It has a vertical asymptote at x equals 0. It's always continuous. I don't have to pick my pencil up or my pen up. And it is the reflection of y equals a to the x. It should be y equals a to the x about the line y equals x. Okay, so the important things to remember, again, one last time, and I'll shut this video off, but we say there's a vertical asymptote at x equals 0 on the parent function. There's an x-intercept at 1, 0, and it grows very slowly. I'll put an exclamation point on that one. Cheers.